For millennia, humanity gazed at the stars, those distant pinpricks of light scattered across the inky canvas of the night, dreaming of living among them, of traversing the vast gulfs of space that separated us from those celestial wonders. The idea of a home amongst the stars, a permanent foothold beyond our earthly bounds, captured our imaginations. In the 20th century, that dream began to take shape, fueled by technological advancements and an unquenchable thirst for exploration. The space race ignited a fierce competition, pushing the boundaries of what was thought possible. The first space stations, rudimentary as they were, like the Soviet Salyut, a pioneering endeavor in orbital habitation, and American Skylab, a testament to American ingenuity in space, proved humans could live and work in orbit, defying gravity and expanding our understanding of the universe. These early missions demonstrated the human body's resilience and adaptability in the harsh environment of space. These early outposts were cramped and basic, offering limited space and resources, but they paved the way for more ambitious projects, laying the foundation for future generations of space stations. They were the crucial first steps on a long and challenging journey. Mir, launched in 1986, a symbol of Soviet space prowess, was the first modular station, a revolutionary design that allowed for expansion and customization. Assembled in orbit, piece by piece, a testament to human ingenuity and precision, and hosting international crews for over a decade, fostering collaboration and breaking down political barriers. Mir became a symbol of unity in space exploration. Mir taught us about the challenges of long-duration spaceflight, the psychological and physiological effects of prolonged exposure to the space environment, and the engineering needed to survive in space. The complex life support systems and technologies required to sustain human life beyond Earth. On November 20th, 1998, a pivotal moment in space history, a Russian Proton rocket launched Zarya, the dawn of a new era in space exploration, the first module of the International Space Station, a symbol of international cooperation and a testament to human ambition. Zarya, meaning dawn, a fitting name for a module that heralded a new beginning, marked the start of a new era, an era of unprecedented international collaboration in space, pushing the boundaries of science and engineering. The ISS was more than hardware, it was a symbol of human potential. It was a promise of global collaboration, a demonstration of what nations can achieve when they work together towards a common goal. It became a beacon of hope after the Cold War, a time of political division and uncertainty, uniting nations in a shared mission, transcending political ideologies and cultural differences in the pursuit of scientific discovery. This launch was the culmination of decades of dreams, years of planning, and countless hours of hard work by engineers, scientists, and astronauts from around the world. The ISS would become the most ambitious construction project in human history, a sprawling complex of modules and equipment orbiting hundreds of miles above the Earth, a home and laboratory for all humankind, a place where astronauts and scientists could live, work, and conduct groundbreaking research in the unique environment of space. Orbiting silently above us, a symbol of human ingenuity and our unwavering pursuit of knowledge. Building the International Space Station, or ISS, was an endeavor unlike any construction project ever undertaken on Earth. It presented unique challenges that required innovative solutions and international cooperation on an unprecedented scale. There were no cranes, no trucks, no heavy machinery as we know them, just powerful rockets delivering essential components and the precise movements of robotic arms, all orchestrated 400 kilometers above the surface of our planet. This distance presented logistical hurdles that demanded meticulous planning and flawless execution. Each module, each solar array, and every piece of equipment was individually launched into orbit, then carefully maneuvered and joined together in a complex orbital dance. The assembly process required pinpoint accuracy and relied heavily on the expertise of both astronauts and ground control teams. All this while constantly traveling at a mind-boggling 28,000 kilometers per hour, circling the Earth every 90 minutes. This incredible speed added another layer of complexity to the construction, requiring constant adjustments and calculations to maintain the station's position and orientation. Astronauts, true pioneers, performed incredibly dangerous spacewalks. Venturing outside the safety of the station, they were guided every step of the way by mission control back on Earth and aided by the invaluable Canadarm2 robotic arm, a marvel of engineering that allowed for the manipulation of large and heavy objects in the vacuum of space. the station grew piece by piece, starting with Zarya, then Unity, followed by Destiny and Quest, and the deployment of vast solar arrays to power this orbiting laboratory. The addition of European and Japanese modules significantly expanded its research capabilities, allowing for a wider range of scientific experiments to be conducted in the unique environment of space. Over more than a decade, more than 100 separate spaceflights were required to assemble the ISS into its final configuration. Thousands of engineers, scientists, and technicians from many nations worked together seamlessly, overcoming technical challenges and logistical hurdles to bring this ambitious project to fruition. The result is a sprawling complex, a testament to human ingenuity, larger than a football field orbiting our planet. The ISS stands as a monument to international collaboration, a shining example of what can be achieved when nations work together towards a common goal. It was built in the most challenging environment imaginable, a place of extreme temperatures, radiation, and vacuum. It stands as a powerful symbol of what humanity can achieve when we pool our resources, share our knowledge, and strive for something greater than ourselves. It's not just a laboratory, but a beacon of hope, a city in the stars, pushing the boundaries of science and exploration. Inside the International Space Station, a remarkable feat of human engineering unfolds every single day. Astronauts from around the globe live and work in this orbiting laboratory, pushing the boundaries of science and exploration. But their very survival hinges on a complex network of systems. Survival in this unforgiving environment depends entirely on engineering a self-contained world, a miniature Earth floating hundreds of miles above our planet. Every breath, every drop of water, every degree of temperature is meticulously controlled and managed. The heart of this artificial biosphere is the Environmental Control and Life Support System, or ECLS-S, a marvel of closed-loop technology. This intricate system tirelessly manages the air the astronauts breathe, the water they drink, and the temperature that keeps them comfortable. It's a delicate balancing act, mimicking the Earth's natural processes within the confines of a spacecraft. Oxygen, essential for life, is ingeniously generated by splitting water molecules through a process called electrolysis. This process separates water into its constituent elements, hydrogen and oxygen, providing a sustainable source of breathable air. Simultaneously, carbon dioxide, a byproduct of respiration, is constantly scrubbed from the air, preventing it from building up to toxic levels. Advanced filtration systems capture and remove this waste gas, ensuring a safe and breathable atmosphere. In the spirit of maximum efficiency and resource conservation, nearly every drop of water is meticulously recycled. This includes water recovered, even from sweat and urine, transforming what would otherwise be waste into a precious resource. This remarkable feat is achieved using advanced purification systems that employ a combination of filtration, distillation, and chemical processes to ensure the water is safe and potable. The station's closed-loop water system is a testament to human ingenuity, minimizing waste and maximizing resource utilization. This self-sustaining approach is vital not only for the current mission, but also for the future of long-duration space travel and deep space missions where resupply from Earth is not feasible. Maintaining a stable temperature is also crucial. Temperature extremes are carefully managed by layers of specialized insulation. Excess heat is dissipated into space by an external cooling system that utilizes large ammonia radiators acting like giant heat exchangers. Through these sophisticated systems, the ISS maintains a comfortable and habitable environment for its crew. This is no small feat considering the violent extremes of temperature, radiation, and vacuum that exist just outside the station's walls. Every single system, from air revitalization to water recycling, is a marvel of engineering, representing the pinnacle of human innovation. Together they work in harmony to keep astronauts alive and thriving in the otherwise deadly vacuum of space. Beyond their immediate life-sustaining functions, these technologies serve as crucial testbeds. They are paving the way for future missions to the Moon, Mars, and beyond, pushing the boundaries of what's possible in space exploration. In the vast and unforgiving expanse of space, the ISS stands as a tiny, stable haven, a testament to human resilience and ingenuity. It's a beacon of hope, demonstrating our ability to engineer life support in even the most extreme conditions, and a stepping stone towards a future where humanity can thrive among the stars. The ISS relies entirely on solar power. Its vast golden solar arrays, visible from Earth, convert sunlight into electricity. As the station orbits, the arrays track the sun, maximizing energy capture. During each 90-minute orbit, the ISS spends half its time in sunlight, half in darkness. Excess energy charges massive batteries, which power the station during orbital night. This seamless cycle ensures life support and experiments never lose power. The solar arrays and batteries are the lifeblood of the station. Without them, the ISS would go dark in minutes. Harnessing the sun keeps humanity's outpost alive. Life aboard the ISS is a blend of science, maintenance, and daily routines. Astronauts' days are scheduled to the minute from wake-up to lights out. Hygiene is a challenge. Water floats, so even brushing teeth is different. Most of the day is spent on experiments and repairs, supporting research only possible in microgravity. Exercise is essential, 2 hours daily to counteract muscle and bone loss. Evenings bring shared meals, video calls home, and time gazing at Earth through the cupola. These moments of connection and reflection are vital for mental health. Astronauts adapt, thrive, and find meaning in their orbital home. The ISS is a unique laboratory offering continuous microgravity for groundbreaking research. Scientists study how the human body adapts to space, gaining insights into bone loss, muscle atrophy, and disease. Materials science benefits too. Without gravity, alloys and crystals form more perfectly. Protein crystals grown in space help design new medicines for diseases like cancer and Alzheimer's. The ISS also monitors Earth, tracking climate change and natural disasters from orbit. Astronauts capture stunning images, deepening our appreciation for our planet's beauty and fragility. Every experiment expands our knowledge, both for future exploration and life on Earth. The ISS is a bridge between worlds, advancing science for all humanity. Its discoveries shape medicine, technology, and our understanding of the universe. Microgravity research is the ISS's greatest legacy. The ISS is the ultimate symbol of international cooperation. 5 space agencies, NASA, Roscosmos, JAXA, ESA, and CSA, joined forces to build and operate it. Each partner contributed unique modules, systems, and expertise. Mission control centers worldwide coordinate the station's complex operations. Crews from many nations live and work together, transcending cultural and linguistic barriers. On board, they are a unified team, not just representatives of their countries. The ISS proves that collaboration can overcome political and cultural divides. Even during tensions on Earth, the station remains a beacon of unity. Its success is both scientific and diplomatic. The ISS shows what humanity can achieve when we work together. The ISS is evolving into a hub for commercial and future exploration. Private companies are testing technologies and planning new modules, paving the way for a sustainable space economy. The station is a training ground for missions to the Moon and Mars, testing life support, radiation shielding, and crew health. Lessons learned here are critical for future deep space journeys. Commercial modules and free-flying stations are on the horizon, expanding humanity's presence in orbit. The ISS is a catalyst for this new era, inspiring innovation and growth. Its eventual retirement will mark a transition, not an end. The knowledge gained will shape all future space habitats. The ISS is our stepping stone to the stars. The ISS is more than metal and machinery, it's a symbol of what we can achieve. For over 2 decades, it has been a place of peace, discovery, and unity. Its scientific breakthroughs improve life on Earth and inspire future explorers. The station has changed our relationship with space, making it a place of work and home. Its greatest legacy is as a beacon of international cooperation. The ISS orbits above as a reminder of our shared humanity. When we look up and see its steady light, we see our own potential. The ISS is our first city in the cosmos, a testament to teamwork and vision. It lights the way for all future journeys beyond Earth, a legacy written in the stars, inspiring generations to come.